This isn't even on, is it? It doesn't matter, you have it in front of you. Okay, yesterday we talked about Taylor polynomials, right? To approximate a non-polynomial function. Now, is it going to be exact? No. We're using a polynomial to approximate another function, and so we're going to have a little bit of error. Now, it's going to be exactly the same at that point, but as we move away from where our polynomial is centered at, we're going to have some error, okay? So like flashback to some of your favorite classes, Calculus 1. Do you remember when we graphed a curve with a tangent line, and then we would ask you to use that tangent line to approximate another value, right? The further you got away from the tangent line, the less accurate we were, okay? Same kind of concept here, where you, except we're talking about a polynomial approximating a non-polynomial function, all right? So we are going to talk about the error bound for these Taylor polynomials, and it's called the Lagrange error. Now, Lagrange, I think, got the credit, but Taylor also figured it out too, and so it says it's also called Taylor's theorem remainder, but really it's called Lagrange because he got it first. So here we go. Our function that is not a polynomial, we write a polynomial for it, and then there is some remainder to account for the error that we would add on, right? So essentially our remainder is the function minus the polynomial, right? Now, this is what our remainder is going to look like. When we talked about alternating series, our remainder was what? If I talked about the sum of the first three terms, our remainder would have been the fourth term, okay? Same concept is going to apply for these Taylor polynomials. The error is going to be similar to the next term, essentially, except it gets a little bit more complicated, okay? So you can see that this is our error bound right here. You can see that it follows the model of, the next derivative over n plus 1 factorial times x to the n plus 1. Okay, and it has this x minus c because we're not always centered at 0. So this is just accounting for where we're centering at. But there's something kind of weird here with that z, right? Okay. Basically what's happening is, yes, this is the next term in our polynomial, except we want this to be maximized, okay? To really account for that error bound, we need to make sure that we're making our remainder as big as it could be, all right? So z is going to be the z is the x value on either x to c or c to x that makes the maximum value. Okay, and I'll show you how to do that. Sometimes they're going to give us that. Sometimes we're going to have to figure it out. But things like a sine or cosine graph, we know what the maximum value would be on that graph, right? Because it bounces between two different numbers, okay? Or like a parabola, we can easily identify what the maximum would be there. Every time we talk about the Lagrange error, we're going to talk about an interval. So if it's a function that continues to increase, well, the maximum would occur at the end of the interval. You see what I'm saying? here. So those are things that we will think about. Essentially, we want to think of this as the next unused term, all right? But we want that derivative to be maximized, right? Any questions so far? Okay. We want to be sure that we have the most error accounted for. Okay. So, go ahead and turn the page. We're going to look at example 1. Okay, this is one type of problem you're going to see. This one is interesting because it kind of gives you the maximum for that next derivative. Okay. All right. So we have a fifth differentiable function. So all 5 derivatives exist. That's important, right? On the interval from 2 to 3. Our fifth derivative is at most 0.2 in that interval. And the 4th degree polynomial is used to estimate f of 3. Okay? First of all, where is this centered at? Okay, so our center is 2. Okay. We are using a 4th degree polynomial. Okay. So I'm going to go ahead and I'm going to do kind of some weird notation. So our polynomial that is a 4th degree, we're going to plug in 3 to estimate f of 3. That is essentially what we are doing. Okay. So the remainder. I'm going to use R for remainder. Okay. The remainder for this 4th degree polynomial, okay, we decided was going to be the maximum for, since this is a 4th degree polynomial, we're going to talk about the 5th degree polynomial, the 5th derivative of z, over 5 factorial times x minus 2 to the 5th. Right? That is going to be our remainder. Do you agree? Okay. Now, this is centered at 2, and we're using it to approximate 3. So we have moved away from the center, which is why we're going to have some error. All right? Now, we know that this is going to be less than, we know that the maximum value for that 5th derivative is going to be 0.2. Okay, we know we have 5 factorial. And then since we're approximating R of 3, okay, go ahead and put a 3 here now. We're going to go ahead and make this 3 minus 2 to the 5th. Okay, we put absolute values on there because it could be negative, right? We have alternating. Okay, so what do we know? That I wrote really large, I'm sorry. Our remainder at 3 is less than or equal to, we have 0.2 divided by 60 times 1. Okay. Well, we can use a calculator, so it doesn't matter. Take 0.2 divided by 5 factorial times 1. Yes.
The equation on the right,
Yep.
It's the same thing as the equation on the left with the values plugged in.
Yep.
So z would be whatever they gave you at the top.
Well, see, they gave us this 5th derivative will be less than 2.
Then why are we looking at the 4th derivative?
We're not.
But as far as 4 is not.
Yes. So since we have a 4th degree polynomial, we look at the fifth term for our error. Well, fifth derivative over 5 factorial times x minus e to the fifth. It's like our next unused term, just like we did with alternating series.
I'm sorry, I'm getting a lot of vocabulary mixed up.
So our polynomial is of fourth degree.
Okay, so piece of 4 is basically the fourth. It's basically the 4 term.
It probably has 5 terms, right? There's probably like a constant plus something times.
Oh, okay, so something to the 4th with 3, okay, and f of 3, and it's approximately.
Okay, so we have a function and we have a polynomial of fourth degree approximating that function. Okay, when we plug our polynomial is centered at 2, which means when we plug in 3, it's going to be slightly off because that's not where it's centered at.
Oh, that's.
Okay, so we're looking at what's the maximum we're going to be off by. Okay. So you ready to punch that in a calculator? 0.00167. It's not very much, right? Okay. So this is what it's saying. When we plugged in 3 to our polynomial, we got 1.763. So what's the interval that f of 3 would have to be in? Okay, so our approximation was 1.763 and our error is 0.002 if we round to 3 decimal places. So we have an interval, 1.763 minus our error, and and 1.763 plus our potential error. So f of 3 would actually reside somewhere in the interval 1.761 to 1.765. Okay, our error isn't that much. All right, so we have a pretty good approximation of where the actual f of 3 will be based on our polynomial. That's pretty cool, right? Okay. I know we're talking about a polynomial that we can't see, but I wanted to focus on the error first. This means belongs to.
Okay.
There's some math notation for you. Okay. Has anyone seen that symbol before? No? Who's going to take math beyond calculus in college? All right, get used to that symbol. Belongs to.
Do you not do like a inequality?
Oh yeah, you can do that. Yes.
So back to this equation, since we were using a fourth degree polynomial, we used the fifth derivative.
Yes.
But if we had a third degree, we use a fourth derivative.
Yes. Basically, whatever degree. Oh my goodness. Whatever degree your polynomial is, the next term would be your error value. Okay. So based on that, could f of 3 equal 1.778? No, why not?
0.002 is the maximum error. Correct?
Okay, so it doesn't fall in that interval that we just wrote down. Okay. What about 1.764? It could equal that because it does fall in the interval that we just calculated. Okay.
Is that like good enough justification? It falls in the interval once before.
Yep. Okay. What I would like you to do is I would like you to go turn to example 2. In example 2, we need a 5th degree Maclaurin polynomial for sine of x. So I would like you to find that for me. Find me the 5th degree Maclaurin polynomial for sine of x and then stop. Don't take up all of that room because we have more to do after that. I know, Bailey, I'm sorry.
Ended at 0, I'm guessing. Um,
Okay. So I just got an email that the award of excellence is Thursday during this class.
Oh, no.
And we have a quiz. When we're done with these notes, we're going to have to make a game plan here. What's our polynomial?
X minus x cubed over 3 factorial plus x to the 5th 5 factorial.
You agree with Josh?
Yes.
Excellent. So this is approximating the sine of x.
Should we leave it with the factorials or if we want to put it as a
I accept either way. Okay. Now, use your polynomial to approximate the sine of 1. All right. So the sine of 1 is going to be approximately our 5th degree polynomial with 1 plugged in. Okay, obviously this is centered at 0 because it's a Maclaurin polynomial. So when we plug in something other than 0, it's an approximation, right? But this is an easy approximation. Okay, we can't do the sine of 1 without a calculator, can we? No, but we can plug 1 into a polynomial pretty easily without a calculator. 1 minus a 6th plus 1/20th. What is that? 101 1/20, and what did you say?
0.8417.
Okay. That is approximately the sine of 1. Now, we have some error attached to that, though. So let's talk about our remainder. Our remainder is going to be the maximum our sixth derivative could be over 6 factorial times 1 to the 6th. Why did I put 1 to the 6th?
Because it's just X.
Okay, this is technically x to the 6th because we are centered at 0, and so then we're just going to plug in 1 for our x value. Okay, now, let's think about the 6th derivative. What would our 6th derivative be? Negative sine x? And what is the maximum that's ever going to be? 1. So our remainder is going to be less than or equal to 1 over 6 factorial times 1. In other words, our remainder of our 5th degree polynomial at 1 will be less than or equal to 1 over 720, or 0.00138. Yeah. So the sine of 1 would have to be between our approximation minus the error and our approximation plus the error. Yeah.
So for the remainder, the top value in the numerator, why wouldn't that be 0 since the 6th derivative at 0 is 0?
Because we aren't talking about 0, we're talking about an interval like 0 to 1. Okay, like we've moved away from 0. So we have to think about what the maximum would be as we move away from where we're centered at.
How do we know it's 0 to 1 then?
Because, well, it's centered at 0 and we're approximating at 1. Okay, now I know that negative sign is going to get dipped down first, right? But it's the absolute value, right? And so -1 positive, it becomes +1. Now, is +1 like a little bit of an overstep? Yeah, because it doesn't happen until pi over 2, which is a little over 1. But that's okay because 1's an easy number to calculate with, okay? Anytime you have the sine or cosine graph, you're going to want to just use the amplitude to make it easy, okay? That's going to be the maximum, excuse me. Okay, so part C, could the sine of 1 equal 0.9? No, because that's not in our interval. How do you feel about this?
Not too bad.
Not too bad?
Not too bad.
All right.
Oh, average.
That's why we just got to work through it. Okay, so on the back you see we have 2 more examples. So go ahead and read through number 3. Number 3 is strict no calculator. Yeah.
How is this useful? Because if we need our calculator to figure out the error, we would just use our calculator to figure out the sine of 1.
Yes.
That's probably how they calculated the previous calculation. Maybe. No?
That's a good question. You might be right, Tyler. I mean, they might have to use like a super long Taylor polynomial, right? But like here, number 3, no calculator. Useful information for you. Okay. All right. So we need a 4th degree Taylor polynomial for e to the x. So some of you have already started working on that. Go for it. Caroline.
So would you say it's not within the range you can foresee?
Yeah, just say it was outside the interval.
Wait, can you probably do like a partial E, is it like, so X only for E, or you say it's part of it?
Well, hold on. First, I want us to focus on the Taylor polynomial, okay? This is like the easiest Taylor polynomial or Maclaurin polynomial ever, right? E to the x, e to the x, e to the x, e to the x. And this is one that we'll eventually memorize the pattern for. Okay? Right? Because it's pretty easy, right? So we have 1 plus 1x to the first plus 1 over 2 factorial x to the second plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth, right? Okay? You're probably going to see this written as x squared over 2 factorial x cubed over 3 factorial x to the fourth over 4 factorial. Okay, and we want to approximate E.
So you don't need like to put E X or like.
That means like this is like E to the first power. Right?
So X is.
Right. So it's similar to what we just did. So E to the first is approximately our polynomial at 1. Okay? So we can easily make these have denominators of 24, right? We have 1 24th plus 4 24ths plus 12 24ths.
4 factorial, 4 times 3 times 2.
24. 4 times 3 is 12 times 2 is 24. Okay, so 1 24th plus 4 24ths plus 12 24ths plus 24 24ths plus 24 24ths is 65 24ths. Our remainder for our fourth degree polynomial at 1 is going to have to be the max of the fifth derivative over 5 factorial times x minus c to the fifth, right? And we wouldn't really necessarily have to write the minus 0, but we're centered at 0. Okay, so we do not have our calculator. Our interval technically is like 0 to 1 because we're centered at 0 and we're approximating at 1. So what's true about our e to the x function? It's going to keep increasing. So where are we going to find the maximum on our fifth derivative? Okay, and our value would be 2.7 something something something. Okay, we're working without a calculator here. What would be a nicer number than 2.7? Well, we're working without a calculator. What about an integer? 3. Because we have an inequality anyway, right? So we're just like, our error's a little bit bigger, but that's okay. This is going to have to be less than 3 over 5 factorial, right? which is 1 over 20.
Wait, so if we said that it could just go on forever, how do we just want to equate it as 1?
What do you mean equate it as 1? So, okay, so we're only looking at, this is centered at 0 and we're approximating at 1. So really we're looking at the interval 0 to 1. Now it's increasing on that interval, and so our maximum is going to occur at the end, which is 2.7 blah, 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 blah. But since we're without a calculator, we're just going to say it's 3.
Okay, well, if we don't know that, where are we in this community?
Yes.
Should it be 1 over 40?
Yeah. You gave me 3 over 120,
Yeah.
and I wrote 1 over 120. So 1 over 40, is that what you said?
Yeah.
Okay. Thank you. All right, so e to the first is somewhere between 65/24 plus 140 and 65/24 minus 140. I'll go ahead and do that fraction stuff for you.
On the test, would it be okay if we just got to as 2 separate fractions?
On like a non-calculator part.
Yeah.
I mean, technically the AP test doesn't get upset about not simplifying, so that would be fine. With the calculator, though, I would expect those to be combined.
Okay.
Okay. All right. Questions on example 3? Feeling good? All right. A function has derivatives of all orders, and it gives you all of the derivatives. I want a 3rd degree polynomial about 2, and we're going to use it to approximate f of 2.3. Okay, so this is cool, right? Our Taylor polynomial, so f of x, is approximately our Taylor polynomial of 3rd degree. Is that what it says? 3rd degree. So what is our function value at 2? So we have 6 plus our first derivative. So 4 times x minus 2, because we're centered at 2, right? Plus, we have negative 7 over 2 factorial, x minus 2 squared. Plus, our 3rd derivative is 8, so we have 8 over 3 factorial times x minus 2 cubed. Okay, isn't that cool? It just gives you all the values, you just have to plug them in. Okay, so let's make this look a little bit nicer. We have 6 plus 4 times x minus 2 minus 7 halves times x minus 2, the quantity squared. Plus, I'm going to reduce this to 4/3 times x minus 2, the quantity cubed. Okay, so now we're going to use this to approximate 2.3. This is centered at 2, so when we plug in 2, we get an exact value. That's no fun. We want to approximate 2.3. It's pretty close to 2, so we should get a pretty good approximation. So what I want you to do is plug in 2.3 to that polynomial. What's going to happen every time you take 2.3 minus 2? You get 0.3. So in your calculator, 6 times 4 times 0.3 minus 7 halves times 0.3 squared, etc., etc. you have something for me, let me know.
6.921.
6.921. Agree with how they call? Great. So, in the next portion, awesome, they give us that our fourth derivative will always be less than or equal to 9 on the interval 2 to 2.3. So we want the Lagrange error bound of this approximation and an interval that our approximation would be in. So, our remainder for 2.3, okay, so we use a third degree polynomial, which means our remainder is going to use which derivative? The fourth derivative over 4 factorial. What goes here to the fourth power? Okay, we need to take x minus our center. So yes, 0.3. Now, luckily, we know what our fourth derivative max is, so we can just say this is 9 over 4 factorial times 0.3 to the 4th. So it has to be less than or equal to that. So with your calculators, please find me what that value is. Okay, so if our error is less than or equal to 0.003, then our approximation for f of 2.3 would have to be between 6.924 and 6.917. Would f of 2.3 be equal to 6.992? Is that a possibility? No, because it's not in that interval, right? All right, ladies and gentlemen, there's Lagrange error. I will tell you, the AP test will throw it in your face. Yes, you can count on a Lagrange error. Potentially like 3 questions, because there's a pretty good chance it is going to be in a free response question, and then you'll have a couple in the multiple choice. Now, we'll get to some AP questions eventually, but you will for sure have 1 AP question out of the 6 that involves series, hands down. Whether it's Taylor series or whatever, you're going to have one. So let me go ahead and stop.